Here's our schedule for today. I have a couple comments to go over with you concerning the textbook and so forth. And then we're going to talk about free fall a little bit. There's a homework assignment, and this is a regular homework assignment that'll be translated eventually into points on your semester grade. And here comes Yaz. Hey. Here's the SI schedule, and the next one is for today at 2:30 at the Teaching Academy, room 322. And I'll try to have this up every day, so just to remind you of the schedule and so forth. Okay, the textbook website, grtep.com. You can go straight there and purchase the textbook if you care to do so. It's optional. And it now is configured for more than one section. Here's what it looks like for our section. It's in this pull-down menu, and there's sections left over from fall when we switched over to this new system. And then if you look below there, you'll see there's a section set up for the online class. Okay, so you guys here in the lecture hall join the one that says section 0001. And then the online guys are going to go to the one that says 0W59. All right, and that's if you choose to do that. Now, I want you to prepare your iClicker for clicking if you have it. Some of you are already good. Press and hold the power button until the upper that should be upper left rectangle, flashes, and then type in the frequency DD. And if it's already on DD, you're good. And then you'll get the Go Nitro message, and then it'll say ready. Question? Probably this week. I just got the rosters to synchronize adequately about half an hour ago. So I got a little catching up to do, but I won't forget. All right, so here's your first question. Ready? Multiple choice. Skateboarding pooch. 2 events. What's the distance between those 2 events? Has anybody ever seen a dog skateboarding? I mean, in real life and not in YouTube or anything? I wish I could see that one time. It's kind of cool. You guys are really quiet. Like you're hypnotized or something. And it's not Monday, so you can't say that you're. Does anybody have in the next week from Monday yesterday until next Sunday, it's your birthday? Raise your hand if it's your birthday coming up. Okay, good. All right, let's sing happy birthday. Happy birthday to you. Happy birthday to you. Come on, happy birthday, happy birthday. Happy birthday to you. All right, now that's better. All right, 10 seconds to vote. Five, four, three, two, 1, 0. And let me remind you the way that this software works. You can click till your heart's content, till your next birthday. But if you're not registered, I don't know your clicker from Adam. All right, so and on the software, it just shows up as a red clicker ID number. I know the ID, but I don't know that it belongs to you until you register. So you'll get the Go Nitro message and check marks and stuff. Let me close the question here. Yep, you guys are geniuses pretty much. 72% of you got this right. You'll get those indicators, but it doesn't mean you're registered, right? You got to register in web courses. All right. Here's the calculation in case you got tripped up. A few of you did. It's just delta x, the change in the position, xj minus xu. The x coordinate of event j, which is 3.93 meters, and the x coordinate of event u, which is 2.50 meters. And in general, a generic quantity j, delta j, is the later value of j minus the earlier value of j. So whatever it is you're delta-ing, it's always later minus earlier. All right, let's do another question. Multiple choice. You're going to do a calculation here in a second. Okay. What's the elapsed time between the two events? 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Yeah, 1.4 seconds. Actually, let me see what you guys. Yeah, you did good. You did good on that one too. And this one, oops, let me go backwards. Here's the calculation for it, delta t, t subscript j minus t subscript u, 4.6 seconds minus 3.2 seconds. So that gets you the delta t, the elapsed time. I'm getting a little bit irritated now. You guys are not sitting in the first 6 rows. I can see you grinning at me back there with the baseball hat on backwards. Yeah, try to sit up towards the front. I mean, I don't want such a small group as this. See, look at that. Come on down to the front. Come on closer down to the front. I'm not going to embarrass everybody, but all right, just sit anywhere in here now. Make yourself at home. Very good. Okay, good. Just makes things easier for everybody. All right, so that's question number 2 for today. Now we're going to do a numeric answer. And so what I want you to do is hit the refresh key. All right, and the reason for this is a numeric answer. You're going to type in numbers and maybe a decimal point, and the decimal point, and the way it works is it's going to, when I start the question, you're going to be on number 1. And the other numerals are above and below that. So like an old-fashioned cell phone where you have to hit the 3 key, like 3 times to get the letter F. Same thing with the numerals and stuff on this baby. All right, so here's the question. Calculate the average speed. All right. Now hit your refresh key if you're not on the number 1. Raise your hand if you got the number 1 on your display. Okay. All right. If you don't have your clicker, you'll have to wait till you get your clicker. All right. So just calculate your average speed. Take a minute to do that. Now we're going to be doing, this is a pretty simple calculation, but we're going to be doing calculations, and some of them are going to be a little bit challenging. And when you're in lecture here, I want you to definitely collaborate with your neighbors. So sit with somebody you know, or make a friend with somebody in class. And then, and just talk during lecture. No, not while I'm talking, but when you're doing calculations like this, and granted, this one's not that fancy, but you'll be challenged with other calculations and even multiple choice questions that really make you think. And it'll be helpful if you have a friend to help with that. And I see a bunch of you with the correct answer, but it's not the most popular. Now it's the most no, now it's tied for most popular. I don't understand what. Okay. I'll give you another 45 seconds. And don't forget to hit the send key. If because the clicker doesn't, my software doesn't know what you're typing. It's expecting you to make the decision about what number you send. 1.2 or 1.19 or 1.187. And so you could type in those, could all three of those could be righteous answers for a question, and you want to send them, but I don't see what you type until you hit the send key. So you have to, it's like saying, type in your letter, type in your numbers, and then hit the send key to signify this is my answer. Okay. Otherwise, you won't have an answer in the books. You won't get a check mark. All right. We went over 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what we got here. Yeah, most of you got it right. Answer is 1.02. And let me see if there's any 102s here. Actually, there's the answers. It's kind of hard to operate this display. So there's a correct answer, 1.02. Get my cursor over here. Come on, baby. Here we go. All right. Now, let's see if I can move this downward. .99. See, 1.021. That's a little bit too much. Too many digits, but it's probably righteous. And the reason that I specify how much round off, I see, and when you're doing an exam, I'll be looking at all these values in a spreadsheet. So here's somebody that might have forgotten the decimal or might have missed the decimal point right here. But when you guys have these for test questions, I'll look at your answers in a big spreadsheet, and I'll be able to tell, okay, somebody typed in 102 instead of 1.02, and I'll know to give them partial credit. So instead of 3 points, I might give them 2 points because they flubbed up the decimal point. And or some other error that I can spot. Now, I can't always do that, but a lot of times I can. And the reason that that's nice is that on a Scantron test, you can't do that. I mean, the dot's either the right dot or it's not. But on this, I can look at what you're actually trying to type. And we're going to do some more clicking here with our next, get my cursor over here, question. All right, now we're going to type in letters. All right, so switch modes again, hit the refresh key. And this one is, when I start this next question, it's going to start you at the letter A, I believe. All right. And this one's kind of a goofy practice question. Here it is. Come on, baby. All right. Describe a decision you would make concerning snacking activity. Type in the letters that form your answer. In other words, for example, CBA stands for Sharks Consume Cheetos. Okay, then hit the send key. All right, so you could do that now. So just make up something, this is kind of like a goofy Chuck Norris question. But we can actually use this questioning method for a valid scientific question, in which you type in a code to signify something about free fall, or something about the force of gravity, or anything like that. So this one you can just type in something about your BFF, Justin Bieber, and I'll be able to see whatever you type. Matter of fact, I'm going to look and see. No, don't type in CBA. I already did that one. Type in your own. Don't copy. Gosh. AHI. Cheetos never run. Good. AHJ. Cheetos never walk. Well, that's certainly true. Throw there. I see. Cheetos run sharks. Huh? Can I do what? Oh, that's in the way. Yeah. So we're just doing a fun one here. Okay, 30 seconds starting now. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Notice anything about that photograph? Notice anything about the sign? It says French fries. What about the, notice anything about that? So this is up in Burlington, Vermont, Al's French Fries. Famous sign. Notice anything about it? No? Uh, It's not spelled right. Al made the sign and he didn't know how to spell. Anyway, so they've kept it that way for a long time. All right, let's take a look at your guys' answers, see if there's anything good. Um, oops. There we go. All right, let's go down the list here. Yeah, everybody's starting with Cheetos. Let's go down. What's the Justin Bieber? Let's see if anybody started with N. I hope not. Why? Because Justin Bieber's a dweeb. CGBA. All right, let's see what CGBA is. Sharks always consume cheese. Well, everybody knows that. Good. Let's check some of these up. Uh-oh. I. Let's see if anybody's got the letter N. Oh, yeah, HLN. What? Never mooch. Justin Bieber, yeah, don't even go. Don't even go. Take it easy, son. Take it easy. Easy does it. All right, so anyways, we got a bunch of goofy things. Now, that's all, fun and stuff, but let's do it. A scientific one about free fall now. So this will be serious. All right, and I'm going to give you a code table, bunch of letters A through Z about free fall. Did you ever see this guy, the video of this guy jumping out of this thing way high up? It's like a spacesuit he's wearing, but he's parachuting. He's in free fall. It's unbelievable. Anyway, here's your question. Describe the motion of free fall. Come on. There we go. All right. And type in, read through the code table and try to make something that is true. All right. And this is it seems kind of dorky and stuff, but it's actually a helpful exercise. Putting together concepts You think about it, that's what scientists, that's what everybody does. They put together concepts into a sentence, and hopefully it'll make sense to somebody. Describe the motion of free fall. So just make it as short as you want. And on a test, if I give you a question like this, what I'll do is I'll break down your string of characters, your code. I'll transform each letter into a word from the table, and then I'll put all those words together into a sentence, and then I'll read the sentence and grade the sentence. So it's a way for you to put together some kind of a sentence with 14 character limit that we have for clickers. Do not sit that far back, please. Are you in my class or the next class? Okay. All right. You can sit there for today. Don't sit there Thursday. What's that? Oh, you mean on a test? Yeah. We'll do some of these in lecture as well. This was just but this is a legitimate scientific question, and admittedly, you guys haven't really studied free fall with me yet. That's what we're going to do today. But it's a legitimate thing for me to assess what you're thinking and how you put things together. It's quite revealing. So let me see what we got here. Let me. Yeah, it takes a little time. See some of these. Wow, this is a long one. Huh. All right. 45 seconds to finish. And don't forget to hit the send key. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And don't put your clickers away because we're going to do some other clicking. This is not the last question. Uh, Here's some answers. Let's go down towards the middle. AYPN. Speed moves faster, accelerating. Okay, that's true. Faster and accelerating, that's definitely a concept. BCH, direction is constant. Yeah, that's good because gravity is always downward. It's never horizontal. So you can see that putting in and this is a very simple exercise, but you can see that you can type in a sentence that's true or form a sentence that's true, which is what we humans do, not just in science, but everywhere. All right, so let me blaze this back over here. All right, and let's keep going. Now let's talk about a little bit more detail about free fall. Question? No, you can use up to 14. So you can't write a sonnet, but you can. But using the code, you can actually the code. You could write a haiku. You know, you couldn't write a sonnet, but using the code, that'd be kind of fun. Write a physics haiku that's also true using the code. Boy, that would be tough. All right, now, important concept. This is where we're heading today, free fall. Um, we're going to try to tackle this by the end of lecture today. Galileo, it's pretty important what he did. He chose free fall as the simplest accelerating system that a person could study, and he used it to model all accelerating systems, and it's really good that he did. For instance, he could have chosen friction, a frictional system, rolling something across a floor or shoving something across the floor. But he didn't do that's accelerating. It's decelerating, whether it gets rolled or shoved. But he chose free fall, just like these guys jumping out of a perfectly good airplane. Can you imagine the rush? Man, hey, raise your hand if you've ever parachuted out of a plane, skydove. Oh my goodness, man, that's something else. Now we're going to build up the concepts for this gradually, and I want everybody here to, not to, I had a student ask me, well, Dr. B, I'm not that good in science, but I'm in this class, but let's just remember, we're going to be building stuff up step by step, easy, nice and steady. Okay, and what I want to talk about first here in this regard is average and instantaneous velocity. Average is based on a finite number of position and time measurements, just like the exercises we did with event U and event J with the skateboarding hound dog. Okay, we had 2 positions, we had 2 time measurements, and from that we got an average speed. But you don't necessarily know the speed of the hound dog or anybody else at some intermediate time, okay, unless you have a list of all his speedometer readings, and that, like for instance, my brother's an engineer out in Detroit for the automakers, and they record, and they do these, quarter mile tests and all kinds of endurance testing, and they record everything in a big table, big computer files. But if you don't have that, if you just have 2 positions and 2 time measurements, all you can do is an average. Okay, so for instance, um, the guy, could have, you don't know, what somebody's doing between, the starting time 0.00 seconds and 0.74 seconds. Could have been any speed along the way. All you know is his average, or he could have taken a break, and then sped back up. He could have stopped at the toll plaza on the way down the turnpike towards Miami, stopped to get some Cheetos or something like that. So, and it's basically the same as the fable of the tortoise and the hare, which I mentioned in the textbook, chapter 1.11. There's also an example in chapter 1-10 about the Turkey Lake Service Plaza example on the turnpike. So let's talk about tortoise and the hare. There's 2 dynamical ideas in that. It's a fable. It's not really a physics problem, but you can say physics concepts concerning the tortoise and the hare. Okay, once the tortoise gets going, for instance, his speed at any instant of time is the same as what it will eventually be called as average. All right, so he might have an average speed of 1 foot per minute because he's a tortoise, and once he gets up to 1 foot per minute, and that's his instantaneous speed, and it's also because he keeps it, it's going to be his average speed. Question? No, we're going to keep going. All this stuff is on YouTube, so you can go back and look at it and redo your notes off YouTube. So here's an image from the textbook that I pulled. Um, get my cursor over here, right here. So these blue rectangles signify his average speed, and so he starts out at time t equals 0, and he gets halfway to his top speed, and in 1 second he's at his top speed, and he just keeps and holds it all the way out to the goal. Now the hare, on the other hand, his velocity state changes several times. So these are two different dynamical concepts. One is constant velocity for the tortoise, and one is changing velocity or accelerating for the hare. So the hare takes little naps and stops for Cheetos and donuts and whatnot. And so his graph of velocities might look like that. Right? So he's got some high velocities in there, but he takes too many breaks, and so he gets he gets beaten by the tortoise. The tortoise just keeps on going, just like a Timex watch. All right. And so in terms of the instantaneous speeds, v of t is how you would pronounce that. V of t is a constant for the tortoise. Right? So that's again a way of kind of using some mathematics to state this dynamical concept, 5a. All right, and for the hare, v of t is all over the place. So that's kind of a semi-mathematical statement to restate 5b, that dynamical concept. And what we're going to be able to do here by today, the end of class today and Thursday, is write some equations down that are full equations. So 6a and b, those are kind of semi-equations. I start out with some mathematical symbols, but then I finish with a sentence. All right. Now here's something that's highly useful for the tortoise's graph. So here's a tortoise's graph, and he's operating at a pretty low speed. But the nice thing about it is it's mostly rectangular. All right, now that's going to be important for us. All right, and the tortoise is he's the epitome of constant velocity. All right, the velocity graph of velocity over time, which is what we've got here, for an object at constant velocity is going to be rectangular, just the way the tortoise's is. All right, so let's make an abstract graph of constant velocity versus time. Now we're dropping the tortoise and the hare, and we're going all the way into an abstract graph here. All right, so here's the graph. All right, on the vertical scale is the velocity. The upper half, +1, stands for 1 meter per second, and we're going to consider this to be going to the right. The bottom half of the graph, -1, signifies -1 meter per second, and we're going to consider that as going 1 meter per second to the left. All right, so the minus sign in this context gives you a direction and therefore a velocity. This is a velocity graph. All right, now the dashed line tells you the actual graph. Okay, so a horizontal axis represents time, and we usually start it at time t equals 0.0 seconds, but you don't have to. Just start it wherever you like. And we're going to graph this constant velocity object out to t equals 2.5 seconds. And, we're just going to say that it's moving at constant velocity 1 meter per second rightward for 2.5 seconds. Very, very simple motion. Now, 1 meter per second is about 2.24 miles per hour. So this is an easy walking speed. All right, 2.5 seconds. All right, so the graph is this horizontal dashed line up at +1. All right. Now, and just to note to you, it's similar in shape to what the tortoise's graph was. Okay. And here's the important thing for this graph. The graph encodes all instantaneous speeds visually. You know, in geometry class, you may have remembered that the definition of a line segment is all the points directly between the two endpoints. And there's an infinity of points on any line segment. You can't count them. And same thing here. On that horizontal line segment, you have any number of instances of times that you would like to choose. All right. And visually, it encodes or expresses the fact that this object is moving at 1 meter per second. All right. Now, next concept. I want you to shade in the rectangle between the graph and the time axis. So shade that part in right there. Okay, and now it looks like an actual rectangle that's been shaded in. All right. So from 0.0 out to 2.5 seconds, and below the velocity line, the dashed line for the velocity, and above the time axis. So, as I said, the straight line represents really nicely the object's velocity at any instant of time that you may care to measure. But what does the enclosed rectangle represent? That's what we want to think about. I mean, because, you know, remember, Galileo said things are represented by, you know, geometrical figures. All right, geometrical figure, a line segment, that represents the velocity. Another geometrical figure here is the rectangle. You know, does that represent something? Does that communicate? Does that encode anything? You know, because here's, you know, pretty basic concept. The area of a rectangle is base times height. Everybody knows that. You know, that's from like 7th grade math class. Hopefully you remember that. And for this one, what's the size of the base for this rectangle? What would you say is the size of the base of this rectangle? Raise your hand. What do you think? It is. It's 2.5 seconds. What about the height? It's not 1, plus 1, but what else? Plus 1 meter per second. All right, so here's your, all right. So your base is 2.5 seconds. Your height is 1 meter per second. And you know, you can, you know, so whatever the area is, this is how you would calculate it. Now, this is not going to be square meters or square centimeters or square inches, because this is abstract. This is not an XY graph paper graph. This is an abstract graph. Velocity on the vertical, time on the horizontal. We don't have any meters or centimeters in here. We have meters per second in the vertical. We have seconds on the horizontal. So we don't have any, you know, don't think of it as XY graph paper, but do think of it as an area. Now, do you notice anything about that equation? Area equals 2.5 seconds times 1 meter per second. Notice anything? Raise your hand if you notice something that's helpful or handy. Seconds? What about them? Yeah, they're both in there, but they're not in there the same way. Yeah, the seconds cross out or cancel. So go ahead and put a line through them. Bing. All right. All right. So all you're going to be left with is meters. And so it works out to 2.5 meters. And does that make sense? If you're traveling at 1 meter per second for 2.5 seconds, how far do you go? 2.5 meters. All right. So as I said, the tortoise and the hare example has given us a notion to look at this constant velocity graph. The constant velocity graph, this is a Cinci one, and it is easy to interpret. The line segment is the graph itself, but the other geometric figure is the rectangle. The rectangle area represents the distance. So in general, it is kosher to interpret the shaded area between the graph and the time axis as the distance that you have traveled from point A to point B. So he's moved 2.5 meters along the x-axis, or whatever the axis is where he's, going at constant speed. All right. Or you could say he's moved 2.5 meters down Alafaya or down University heading for Dunkin' Donuts. Question.
So basically, you're saying that if it's constant, the velocity of everything is what is the hare you have on the
Yeah, so the hare is going to be a different shape. It won't be a nice, easy rectangle. But you know what is a nice, easy shape is free fall. And so we're not going to try to tackle the hare, but we are going to tackle free fall. Okay, now all this jives perfectly with the distance formula, delta x equals v delta t. V is the height, delta t is the base. So that's we've already seen that. That the area, it was there all the time. It was looking right at us. But now we have this abstract tool, Mr. Henry, and we're going to use it. We're going to use this interpretation for any velocity graph, because you know what we're going to do next? We're going to do free fall velocity graph. Put that together, and then figure out how to get an area for that. And that's going to be really helpful to us, because then we can figure out what's happening with free fall, and how, for instance, how far do you fall in a second time. All right, so let's think about these ideas of position and time. Hit the refresh key again. And this is going to be multiple choice. And hey, you guys, on multiple choice, you do not have to hit the send key. That's why you have to, but you do have to hit refresh to change into multiple choice mode. So hit your refresh key and then just type in A, B, C, or D. And this is a regular physics science question. So each dot represents position. Elapsed time 0.1 second between each flash of, like strobe. So is it speeding up, slowing down, constant velocity, or impossible to determine? 10 seconds starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Let's see what you guys have got here. Oh, there's a little bit of a spread in the data here. Some of you voted for A, some of you voted for B, some for C. The correct answer is slowing down. Now, here's a perfect example of something that I could set up a code question for. Form a sentence to explain why this is the correct answer. But we don't have a code question, so I'll just ask for a show of hands. Who can explain why this has to be true? What about this set of images, A, B, C, D, and E at the bottom, tells you that the object is slowing down? How do you know that? Go ahead. Yeah, the distance between each dot is getting closer. But the time between each dot is 1/10 of a second. So each dot is separated by 1/10 of a second, but you're, eventually down between D and E, you're just kind of poking along there. Right? So it's going to slow down and maybe come to a stop. Right? And that's an accelerating system. All right. So the distances, the speeds. Now let's try to interpret a velocity graph. And this one's going to be a free fall, something that's speeding up downward. All right. So this is you up at the top on the roof of the library and dropping a water balloon over the side. Okay. And it's, the water balloon is going to start from rest, because you're holding it. And then it's going to eventually get faster and faster until it hits the sidewalk. All right. So let's try to. So go ahead and draw a velocity graph. The vertical axis, label it V subscript Y to indicate the Y component of the velocity. So upward half, the upper half of this graph is going to be positive speed. So that means upward speed. Okay, the bottom half is going to be downward speed. So it could be like -2 meters per second in the bottom half, and the upper half you might have 5 meters per second up there. Now we're dropping something downward, so all of our graph is going to be in the lower half of this diagram. All right, go ahead and put in some time markers, and just go out 3 seconds. So the first tick mark there is 1 second. And then, you're dropping the water balloon, and after 1 second, it's going to have some downward speed. So right below that 1 second mark, put in a dot. And make sure you have enough room for another 2 dots, because we're going to do 3 seconds. And this one, here's the actual speed, -9.8 meters per second. For every second of free fall, you get another 9.8 meters per second downward. Right? That's the definition of free. And that's what Galileo was able to measure. Except he wasn't using meters and stuff, but they didn't have the metric system back in his day. I don't know what they used, feet or something, probably, or cubits. Whatever it was, it would have transferred to -9.8 meters per second downward. All right. Now the velocity graph is going to go right through that. All right. So go ahead and poke your velocity graph down there. All right. And run it out as far as 3 seconds. So the right end of that sloped dashed line is right below the 3 second mark. Now I haven't put 3 seconds up there. I only marked 1 second, but the other 2 are implied. Okay. So this point down here is right below the 3 second mark. Okay. Now let's put in a couple other points. All right. So there's 2 seconds. And let's see, that's another 9.8 downward. So let's see, 9.8 plus 9.8, or -9.8 plus -9.8 is, do you guys have your calculators out? Yeah, 19.6, -19.6. Now, if you have graph paper, you can use graph paper for this. And I did this out carefully using pixels and stuff. So here's the last one. And just to the English sentence, we've got it encoded in the graph, 9.8 meters per second downward for every second of free fall. So 3 seconds of free fall, it probably takes 1 point something seconds to get to the ground from the library, top of the library. 3 seconds would probably be like one of those tall buildings downtown Orlando. But anyways, this is what you've got. So what I want you to realize here is that the velocity graph visually encodes what I've written in English in the yellow box. All right, so those 2 things are kind of parallel. One's an English sentence and one's an abstract diagram, and they both encode the same basic situation. All right, now here we go. Now we're not doing the tortoise, but we are doing free fall. All right. And yo, you were asking me about the tortoise, you know, but this is the one that we're going to do. So go to the 1 second mark and let's just shade in 1 second worth of motion between the velocity graph and the time axis. Now, the time axis is above the velocity graph, but we can still shade in. We're shading in above the dashed line. All right. And what that means is now this is going to represent a distance. All right. And it's going to be a distance downward. So you're up at the top of the library, and if you consider the top of the library y equals 0, then the sidewalk is like y equals minus, I don't know, 20 meters or something. Okay, so this area you're going to consider to be a downward drop. And how do you figure out the area of a triangle? What's the formula for that? Remember? 1/2 base times height. Easy. All right, and we're going to use that in a second here. So this is what Galileo was thinking about. This is one of his most famous quotes. I observe a stone initially at rest, falling from an elevated position, not the top of the library, but the top floor of the Leaning Tower of Pisa, continually acquiring new increments of speed. And that was his key breakthrough, or his key insight. And not everybody believed him at the time. Aristotle might not have said it the same way. But he said, yeah, every second of free fall, another 9.8 meters per second downward. All right. And it's acquiring increments of speed. So the increment of speed, go ahead and underline that and write down that the increment of speed, delta V, is negative 9.8 meters per second. All right. And so let's go and now let's take a look at the formal definition of acceleration. Right. Actually, let's talk about the Leaning Tower of Pisa. Has anybody ever been there? Anybody in here ever been over there to Pisa? Did you see the Leaning Tower? A friend of mine showed me a photograph of it, with people down on the ground and stuff. And, and instead of like a diagram, idealized diagram like this, and oh my goodness, that thing is really tipped over. It, did you get that feeling? It's still up. You know what they did? You can't see it in this diagram, but if you look at it carefully, like I was reading, I think it's Scientific American, that, as they put more floors on it, they tilted the floors back the other direction. So this one's tilting to the right, and what they did with the upper floors was they tried to counter tilt the upper floors. So if you look at them really carefully, the floors are all different tilts relative to each other, the upper floors anyways. And you can see it in this one. The top part you can see is definitely tilted a little bit to the left of the main part of the tower. And they tried to do that so that it wouldn't tip over, try to counterbalance it. But I don't know what, in the back, Italy. Where did you go in Italy? Did you go to Venice? Rome, Pisa? You went to Florence? Yeah, that's nice. Florence is very near Pisa. Anyways, yeah, so this thing and so the whole thing about Galileo, the famous dropping, this is a diagram of him dropping a cannonball and a ball bearing or a musket ball at the same time. They don't look different, but that's supposedly the experiment that he did. And he found that each one is another significant thing. It didn't matter what the mass of each object was. They fell and they both landed at about the same time. And he was able to discern that that they, no matter what the mass, cannonball or musket ball or ball bearing, they all fall at the same, delta V, same increments of speed every second. And astronauts, you can't do a perfect test of it here on Earth because of air resistance, but we've done tests of this experiment here on Earth up at, I believe it's up at Langley Research, the NASA Langley Research Labs up in Virginia. They have a big, what do they call those things? Wind tunnel. And in the wind tunnel, they evacuate the air from it. And they can form a vacuum, and then they push through air. So now it's not a vacuum, and they test the aerodynamics and stuff. So they have this one chamber where they evacuated the air, and they dropped a feather and a hammer at the same time. And actually, you can see it on the internet. It's on YouTube somewhere. I'll try to post or link to it in our playlist. But they fall at the same. If you evacuate all the air, it falls at the same time. The other people that did it were the lunar astronauts, the Apollo astronauts. They took a hammer and a feather up to the moon, and there's a famous photo of them dropping both at the same time, and they land on the surface of the moon. Now they seem to float down because gravity's a little bit weaker on the surface of the moon than it is here. It's only about a sixth of what we have here. By the way, the acceleration due to gravity, go ahead and write it down. I don't have it in the notes yet. G, little lowercase g, G equals 9.8 meters per second, or 9.8 meters per second squared. Either one of those is fine. All right. And G is the gravitational acceleration of you, airplanes, a mouse, a cat jumping, from the floor up to the top of the refrigerator, or wherever the cats jump against gravity. Yeah, 9.8 meters per second squared, and it's down, and write down comma downward. And if you're ever doing an equation, you would write it as negative 9.8 meters per second squared, and the minus sign indicating downward. And so, side note to you, that's the acceleration for any object being accelerated towards the center of the Earth. So it's the interaction between Earth itself and everything else. You, your cat, your car, aircraft carrier out in the ocean. And it's the same pretty much everywhere that we humans can go. So most humans, about the highest you can go is about 40,000 feet in an airplane. All right, and G is equal to 9.8. Technically, it's a little bit weaker there than it is at the surface because you're a little bit further away from the Earth. And so top of Mount Everest, 9.8 meters per second squared. The bottom of the Mariana Trench in the Pacific Ocean. If you were in a submarine down there, which they've done that a time or two, 9.8 meters per second squared down there as well. But now the space shuttle, that's about 200 miles up. They're still getting a good acceleration because they'll, if they jumped out of the space shuttle, they'd fall back to Earth. But it's not 9.8 up there. It's a little bit smaller. The further away you get from the surface of the Earth, it gets smaller and smaller until it goes to zero, when you're way out, across the galaxy. But yeah, not everywhere that we go as humans, 9.8 meters per second. But you know, here's an interesting thing about gravity. You can actually, if you have a really, really, really precise gravitometer, a device to measure the strength of gravity, you can actually detect submarines at sea, underwater. You know, so we kind of keep an eye on the Russians, you know, using that. We can actually prospect for metal like gold from airplanes using a or petroleum, you know, gas or stuff. You can, or uranium deposits or any kind of thing that will disrupt the you know, is a little more dense than the surrounding rock. You can pick it up if you have a good gravitometer. And I remember one of my teachers, and goes all the way back to high school. He was a prospector before he became a science teacher. And he said he was retired. He made enough money as a prospector. So he retired to become a science teacher in my high school. But he had all kinds of stories about prospecting. And that's one of the things that they used, the gravitometer, you know, to prospect. He was one of the guys that found the oil up in Alaska, up on the North Slope. So very interesting guy, Mr. Caprio. Long may he reign. All right, so let's talk about the definition of acceleration. All right, it's basically a delta over another delta, a delta t in the bottom, and a delta v, an increment of speed, delta v. You know, a delta, you could call it an increment if you want. That's a synonym. It might not be appropriate every time, but in this case it is. Galileo said that in free fall, you catch the same increment of downward speed for every second. So for free fall, this is a constant. We call it g. All right, and so it's a time rate of velocity change. Okay, and so another thing, if you cross multiply that first equation, you know, delta t, park it over on the left, and then rewrite it, delta v equals a delta t. Yeah, you can figure out how much velocity change you get for a given time interval. You know, so if you know your drop time is 1.5 seconds, and you know that the acceleration is the acceleration due to gravity, negative 9.8, then you know, okay, negative 9.8 meters per second squared times 1.5 seconds. What is that, anyways? What's negative 9.8 times 1.5? It's got to be about 15 or so. Calculation. Come on, calculate. Who's got it? Negative 14 point, negative 14.24, negative 14.25. Is that right? No, negative 9.8 times 1.5. What do you got? Negative 14.7. Is that, anybody else verify that? Okay, so negative 14.7. So in 1.5 seconds, you acquire negative 14.7 meters per second of extra speed. Now, if you start out with some downward speed, that just tells you how much more you got. You know, so if you're already blazing down at 1,000 meters per second, now you're at 1,014.7 downward. All right, and then the area of this triangle we're going to interpret as the distance. And here we go. Here's the formula for it. Just good old 1/2 base times height for a regular geometry class area for us becomes delta y equals 1/2 at squared. And in this, if it's free fall, that symbol a for acceleration, actually we would use the symbol g, and it would be equal to negative 9.8 meters per second squared. And then t squared, that's the square of whatever your drop time is. All right. Now, I'm going to dismiss homework number 1. I set it up over the weekend, and it's now ready to go. Actually, at 12:01, I think it's set to activate. So it'll be due on Thursday. And hey, you guys, homework is always due at the next lecture. So from Tuesday to Thursday, I'll give you a smallish homework. This one's just a bunch of multiple choice. Actually, it has one calculation, fairly simple, and some multiple choice, true, false. But from Thursday to Tuesday, I'll give you a little bit bigger assignments. Anyways, you're dismissed. I'll see you on Thursday. And happy birthday to all you guys that had a happy birthday. What's that name?
I keep getting the stop to cancel time or whatever.
Yeah, no base. It's because you forgot. Did you get here late today?
Yeah, I was here. I bought this like after class Thursday. Last Thursday.
Well, that's not the problem. The problem is you're not on the right frequency. Hold on a second. No. Oh boy, my hip is really sore. Let me stop the YouTube.